Hey Charles, how's it going? Very nice. Awesome. Love it. I love it. Hey Dominic, what's up?
I have a question that's related to heat transfer and it's
Okay.
formula.
Sure.
So I'm designing the firewall.
Okay.
And it has to withstand 60 degrees Celsius.
Okay.
And so I want to make it out of carbon fiber and then put heat resistant tape on the inside.
Okay.
I did it last year and it worked, but I'm not sure how to go about doing the analysis aspect of it.
Okay. Yeah, that's a little bit, can be a little bit tricky. Doing the tape is going to be a little bit tricky. And so do you have like a CAD model for the heat wall?
I don't.
Okay, so that'll be the first step. And so if you get a CAD model for the heat for the wall, then what we can do is we can input like the thermal properties for carbon fiber. And so like thermal conductivity, thermal diffusivity, stuff like that. It's been a while since I've done thermal. And then what we can do is we can input the, I'm guessing this is going to be inside the engine.
It's going to be
or the exhaust.
The engine. It's going to be blocking the engine.
Okay.
Okay. The driver.
Right. Okay. And so what we can do is that, so the engine is going to be outputting a certain amount of energy in terms of heat. Right?
Yeah,
So
they give us a limit that
right.
Be able to withstand.
Exactly. So you can input that as like a boundary condition in ANSYS. You can say that, you know, we have a heat flux or we have like an energy input of like so and such a watts per meter square. And then you can run the simulation and you can check and see if the temperatures exceed, you know, certain you said 60 degrees wasn't
yeah.
Right? Yeah, that's how I would do it, or at least that's how I would start. And so you get a CAD model, put into ANSYS, and then input like a heat flux. And then probably on the other side, you can probably put like a convection boundary condition like ambient heat or ambient air temperature. And then you can see how that is. To do the heat tape, the challenge with the heat tape is that it's so thin. And so probably in like if we were to use a method from 4.7, I would consider that like contact resistance. And then I would do it based on that. But then I haven't done something like that in ANSYS before. So
Dr. Merrill said he thinks it's more of like a radiation type of problem.
Okay. I see. Okay, so the engine is going to be so hot, it's going to be radiating heat.
Yeah.
Okay.
And the tape is like basically just deflecting it.
Oh, okay. Oh, that's interesting. Okay, so the tape's on the inside.
The tip's not like only gonna be on the inside.
Ah, okay. So then the tape is probably reflective in some.
Yeah,
Okay, so it's gonna reflect some of that heat back. Oh, okay. Oh, that's interesting. Okay. I'd have to do a little bit more exploration in ANSYS in terms of how you can do that. But you can do like a radiation boundary condition as well. And so what I would do probably is I would input the temperature of the engine into a radiation boundary condition. And then you would need to have some way of, do you remember in 4.7 we went over the emissivity of the surface? It's like that's
Yeah.
And so you'd have to somehow find a way. Maybe the tape has it kind of listed in their properties in terms of what the emissivity is, and you can put that into ANSYS. But that emissivity of the tape is key to the calculations. Yeah.
Question.
Yep.
So I'm gonna be doing some analysis on the arm.
Yeah.
And I mean, they don't have screws already, but I know because in SolidWorks we gave it relations as if there were a screw there, but there really isn't. So what and if I plug that into ANSYS, would I have to redo those relations again?
For the screws, you mean?
Yeah, for like to make it act as I know with the chair, how we
Yeah.
made it like although these were holes, but there are no screws there, it acted like there were screws there.
Yes. You might not have to because sometimes when you put an assembly in, it might have that information already and it might have the contacts. And so you have to see. And so when you import a part into ANSYS, it'll have like a list of contacts that does automatically. And so you're gonna have to go through each one to see if those are actually the screws that you did. If it's not there, then you'd have to fit them in.
Okay, all right, that sounds good. And also, okay, so the design for the base plate that I have is it's like this, so like the fit, in, lock, and twist mechanism.
Okay.
So it's something like that, like a half circle. And I've already done an analysis on it, but I want to make sure I'm doing it right. Or like if you were to analyze this, what would you go about it? So what I did was because this is gonna be in like a different plate, it's gonna be like this sort of thing. It's gonna have this mechanism in here within the plate like that. Yada, yada, yada. So it's gonna be like this, right? So what I did was I calculated because this was gonna be held still like this amount of material.
Okay.
What I did was I made, because I wanted to calculate the forces, there's gonna be a weight on top of it.
Sure. Okay.
So what I did, I tried finding ways to get it to hold. So what I kind of did was I went about making this outer edge, I believe, fixed plate, fixed support, and then adding the weight onto here.
Yeah, that works.
That works too. Okay. Then mainly I wanted to analyze these. I put the stress on these.
Okay.
But I want to make sure that I was doing it right, or at least it within a reasonable
Yes.
boundary condition.
So it's just on this part that's exposed that we fixed it.
Yeah.
Okay. Yeah. That makes sense.
Let me make sure because I analyzed it. I've been analyzing with like different materials that we want to make out of right now. I still need plug it in and check with nylon, see how that gives, what kind of results that gives me.
I see.
So I just want to make sure because these tabs were because a lot of weight, or at least like around 35 pounds, would be resting on like these like little tabs. They're like about half an inch barely.
I see.
So I wanted to double make sure that my boundary conditions are right for the most part.
Yeah, just be careful because these are so thin. You want to make sure you have these 4 or 5 elements through this thickness right here. Otherwise the stress that you can do may not be. So make sure you put enough conditions.
Okay.
All right, it's 5:30. Let's go ahead and get started. Hi, good evening, everyone. How's everyone doing today? Good, good. Okay. All right, and so we're trudging right along, and so we're going to continue on with our lecture notes on truss elements. Okay? So I think this is lecture 4 in total of finite element theory that we're doing here in the class. Okay. So today will be a good day, depending on if you like trigonometry or not. And so it's probably going to be a little bit more math intensive than our last few days. But I think what you'll see is that when you can add in 2 dimensions, then it kind of opens up your horizons to unlock. All right, and so that's all my announcements. And so all right, and so yes, and so activity 4 was due last night. And so if you're still working on it, you can still turn it in late, except late homework. Just just be aware that I take 10% off each day that it's late. But I know you guys are really busy right now, so just kind of be aware of that. And I'm not going to assign anything else until the project is due. And so after this activity, the reason I put activity 4 in before the project, just because you can use shells and beams for the project. I won't say for which parts you can use it on, but it is possible. So I want to make sure that I have that out to you guys. So if you did want to use it for the project, then you can go ahead. You know how to do it. Okay. But after activity 4, I'm not going to assign anything else until the midterm project's due, and then I'll assign the homework for this stuff. Okay. All right, and so that's all my announcements. And so are there any questions I can answer before we get started for today? Okay, all right, so let's go ahead and continue on. All right, so I'm going to scroll up for just a second. And so, you probably already have this in your notes, but, I don't want to write it down again because it's a lot. Okay. And so we were kind of starting this idea of doing 2D analysis. Okay. And so all we've done so far is just spring finite element analysis and truss finite element analysis, all of them in 1D. But as you can imagine, in 1D, you're very limited in terms of what problems you can actually do. And so we want to kind of increase this to the second dimension, but there's kind of a lot of work that we have to do to get there. Okay. And so the first thing that we're covering here is this idea that you can have different coordinate systems that represent the same thing. Okay. And so the traditional coordinate axis that I think we're most familiar with is the one on the left here, where the x-axis is kind of parallel to the ground. It's purely horizontal, and the y-axis is purely vertical. Okay. But we can kind of rearrange and kind of move and rotate this coordinate axes depending on our needs. Okay. And so one example of this would be like a coordinate axis rotation. So if we were to take this coordinate axis and just kind of take both, and just like as if it were a clock, or I guess a backwards clock, we kind of rotate them counterclockwise, then we can get a different coordinate system that is arranged a little bit differently. Okay? And so our goal for this is that, if we have a vector, and so in this case, we have a vector u, okay? That vector u physically is exactly the same in both coordinate systems. But if we were to describe that vector u in terms of its components in both coordinate systems, their descriptions are going to be different because the coordinate systems are different. Okay. And so what we have is this relationship right here. This is kind of what we ended on. And so what we said is that for the vector u, if we describe its coordinates, ux and uy, in the first coordinate system, we call that the stationary coordinates. It would be ux times I plus uy times j. Okay. For I and j, there are the unit vectors in the stationary x and y directions. This has to be equal to the same vector, but expressed in different coordinates. And so we have ux prime times I prime plus uy prime times j prime, where the big difference here is that I prime and j prime are unit vectors in the local coordinate system. Okay. And so visually they look like this. And so maybe this might help. Okay. And so in the stationary coordinate system, I is like this, j is like this. Okay. Okay, because in the stationary coordinate system, our x-axis is purely horizontal, our y-axis is purely vertical. Okay. But I prime and j prime are kind of like this. So I prime is going to be rotated up just like that. And j prime is going to be rotated just like that. Okay. where the amount of rotation that they have is given by theta. Okay, so that's the difference between those two. So, we have, different unit vectors, and so that's going to lead to different, different representations. But because u here is the exact same vector, we have this equal sign. Okay? And so our goal next is to kind of rearrange this expression a little bit so that we can actually get a mathematical expression between the local and the stationary coordinate system. Okay. Okay, and so what we seek is a mathematical relationship between the stationary coordinate system and the local coordinate system. And so to do this, we're going to form a relationship between unit vectors. So I prime, and j prime. Okay. And we're going to use geometry and trigonometry in order to do that. Okay, let me do this. And so we know the I vector, and I drew bigger here just because we're going to make a triangle from this. We know the I vector here points perfectly horizontal, right? Let me do this. And so let me go ahead and break this up and make a right triangle out of it. Okay. So I'm going to draw one vector that goes in this direction. Okay. A little bit longer, actually. Okay. And another vector that goes in this direction. Okay. So these two purple vectors that I drew them kind of purposely to make them perpendicular to each other. Okay. And the angle at which I drew this at is going to be at the angle theta. Okay. Remember, the angle theta, this is the amount of rotation that our local coordinate system has relative to the stationary coordinates. Okay. 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 And so what this means is that this vector here, or this leg of the triangle, the direction that this leg of the triangle is pointing is, this is pointing in the I prime direction. Okay. Whereas this vector right here, well, this one's actually pointing down to the right, and so this is in the same direction as the minus j prime direction. Okay. Okay, and so what I'm going to do is I'm going to call this the top vector. No, it's black. That's fine. I'll call the top vector A vector. The blue vector I'll call B vector, the bottom vector I'll call C vector, okay? And so using vector addition, so remember when you place vectors kind of tail to head like that, then adding those two will get the third vector right there. Okay, so by vector addition, we can say that the A vector plus the B vector, this is equal to the C vector. Okay. Any questions on this so far? And so this is all just kind of vector, well, this is just vector algebra so far. We haven't used trigonometry yet, but hopefully kind of makes sense about why I drew this triangle the way it is. What we're going to do next is we're going to replace those ABC vectors with the I prime, J prime, and I vectors. But I just kind of want to illustrate to you the vector addition notation. Okay. Any questions on this so far? Right, and so next step that we're going to do is we're going to replace these vectors here with expressions that include I prime, J prime, and I. Okay. We'll do J in a second, but J isn't here yet. Okay, so first thing we're going to do is that if we look at the C vector here, the C vector is exactly in the I direction. And so what we can do is we can set C here exactly equal to I. Okay. Next thing we need to do is express A and B vectors. And so let's do the A vector first. And so we know the A vector here is in the I prime direction. Okay, so let me put I prime here. Okay. But to complete this this expression here, we need to multiply it by the length of that vector. Okay. And so for the I vector, we didn't multiply by length there because we assume the length is 1, right? Because we know I is a unit vector, and so we know unit vectors have a length of 1. Okay. But because of the trigonometry of this problem, the A vector here is not going to have a length of 1. Okay. But what we can do is we can use trigonometry here to determine the length of that A vector. And so the length of that A vector is going to be cosine of theta, right? And then for the B vector, we're going to do the same thing. So we need the length of that B vector. And so the length of that B vector is sine theta. Okay. We know that it's in the J prime direction. Okay. And so we're going to have sine theta J prime. But more specifically, what we set up there is that since that B vector is pointing down to the right, it's actually going to be in the negative J prime direction. So we're going to put a minus sign right here. Okay. So let me put a box around this. And so when we put all that together, we have the I vector is equal to cosine theta I prime minus sine theta J prime. Okay. And so what was the point of that? And so why did we go through all that trouble to look at this expression? Well, now we have an equation here that we can plug in for I. Okay. If we look back at the equation that we saw at the end of lecture last time, we see that we have an I right here. Okay. And so what we can do is we can take that expression that we found and plug it into I here and effectively eliminate one of the variables. Okay. And what you'll see is that if we do that the same for J here, then we'll start to be in business, and then we can actually get something useful out of it. Okay. And so I'm going to repeat the same thing for J, But I'm gonna go a bit faster just for the sake of time. But does this kind of make sense in terms of, how we obtain this expression for the I vector here? Okay, so let's do the same thing for J. Okay, so let me go ahead and draw the J vector. And so the J vector, it points vertically upwards. And then let's form a right triangle out of this in terms of two vectors, one that goes in the I prime direction and one that goes in the J prime direction. So let's do J prime first. So J prime, this. Okay. So we'll call this the D vector. And we'll have another one in that direction. We'll call this the E vector. Okay. This angle right here is theta. Okay. So this D is in the J prime direction. And this E here is in the I prime direction. And so by vector addition, again, we have D plus E is equal to J. Okay. And then once again, we're going to use trigonometry to get expressions for D and E. And so for D here, we have cosine theta, J prime. And then for E here, we have sine theta. Prime. And all this is equal to J. Okay. So now we have these two expressions here, and then just like I mentioned before, we can plug this back in to our U equation from before. Okay, so let me go ahead and repeat that equation here just for the sake of completeness. And so we have ux times I plus uy times j is equal to ux prime I prime plus uy prime j prime. Okay. So that was the equation that we had before. And remember what this equation told us was that if we have a vector u, no matter what coordinate system that we're in, that u is still going to be the same u. And so this is saying that no matter how you express its components, they're going to be the same. Okay. So let's go ahead and plug in for I and j here. Okay. And so if we do that, we have ux times our equation for I here. And so that's going to be cosine theta prime minus sine theta j prime, okay, plus uy. And so I'm going to plug in the expression for uy for j here. And let me swap the terms just for make it simple. So that's sine theta I prime plus cosine theta j prime. Okay. This is equal to ux prime I prime plus uy prime j prime. Okay. So all I did for this step was I plugged in for these. Okay. So we plug in for those expressions and that's what you get. Okay. Let's do a little bit of rearranging here. And so I'm going to rearrange the left-hand side. Yeah. Yes, it is. Thank you. Mm-hmm. All right, so I'm going to rearrange this left-hand side because right now it's kind of grouped between ux and uy. What I want to do instead is I want to group it in terms of I prime and J prime. So I want to have a single I prime term and a single J prime term. And so if we do that, then we get ux cosine theta plus uy sine theta, and all this is equal to I prime, or all this multiplied by I prime, plus we have a minus uy, or minus ux sine theta, then a positive cosine theta uy, is equal to ux prime I prime plus uy prime j prime. Okay. Let's multiply by j prime right here. Okay. Okay, so we just did a little bit of algebraic rearrangement. Okay. So why would I do that? And so I'm going to go ahead and highlight a couple of things to you. Okay. And so on the left-hand side, we have this term right here. Okay. That's multiplied by I prime. Then on the right-hand side, we have ux prime, which is also multiplied by I prime. Okay. Then we also have this expression right here, which is multiplied by j prime. And then this term right here, which is also multiplied by j prime. Okay. What I'm going to tell you is that the terms that are circled there, and they're matching colors, and so the two purple circled terms and the two green circled terms, they have to be equal to each other. Because remember, this whole equation here has an equal sign right here. Okay. And so in order for this equal sign to be true, then those two, we can form two equations for those circled parts. Okay? And so those are two equations are going to be ux cosine theta plus uy sine theta is equal to ux prime. And then we have minus ux sine theta plus uy cosine theta. This is equal to uy prime. So those two equations have to be true in order for our kind of bigger equation to be true as well. Okay. And so I basically just did some terms, just some term matching. So the terms that have the same either I prime or j prime, I just set them equal to each other. And then the next step that we can do, which is what we love to do in finite elements, is we love to put things in matrix form. Okay, because what we have here is a system of two equations, and so we can go ahead and define our matrix from that. And so if we put this into a matrix, we have cosine theta, sine theta, minus sine theta, cosine theta. Okay. And that's going to be equal to ux prime uy prime. Okay. So I put a box around this kind of matrix set of equations here because this is a pretty significant result. Because let's see what this allows us to do. Okay. So first thing I'm going to highlight here is the vector on the left-hand side, the ux, uy. Okay. Remember what these represent. These represent the coordinates of vector u in the stationary coordinates And then this ux prime, uy prime, this is the coordinates of the vector u in the local coordinates. With this extra, cosine sine matrix that we have on the left, we can actually transform in between them. And so what this is telling us is that if we have the coordinates of u in the stationary coordinates, then all we have to do is just multiply together with this matrix here to get the coordinates in the local coordinate system. Okay? And so because this matrix here kind of fills that role of transforming the coordinates, we call this the transformation matrix, T, or just call it transformation matrix for now. And so that transformation matrix is going to be key to doing our 2D truss problems. Okay. All right, so we took kind of a roundabout route, and so kind of a bit complicated, but unfortunately we're only about halfway there, so we still have quite a bit to cover before we can start to do 2D truss problems. Okay. Are there any questions on this so far? Everything that we've done? Okay, so let's go ahead and continue on. And so, why are we going through this? And so why are we, going through this whole trigonometric coordinate transformation, stuff? Okay. The reason we're going through this is that, when we're in 2D, and this is true in 3D as well, we're going to have elements that don't face the same direction. Okay? So this is true for trusses and springs. Okay? So I'll give you an example. And so, let's say that we have a simple, TP. Okay? So we have a 2 truss structure. We have 2 truss bars that are leaning against each other, and they're not in the same direction. Okay, so we have one that's kind of facing up to the right, and another that's kind of facing up to the left. Okay. And so we can solve this problem. Let's say that we're interested in solving for the nodal displacements of this truss. And so we can solve this problem in the same way that we did before. And so what we do is we label the elements, we get the element stiffness matrices, we assemble, we apply boundary conditions, and we solve, right? So that's our 5-step process. Okay. The problem is that when we form the element stiffness matrices for these 2 elements, okay, so we'll call this element stiffness 1. I guess A, because element A, just to be consistent. This will be element stiffness B. Okay. If we were to use the methods that we know before, and so we form the element stiffness matrix as AE over L, 1 minus 1 minus 1, 1 for both ones. Okay. That element stiffness matrix is under the assumption that we're working in a coordinate system local to the element. Okay. Which would be fine, if we were to analyze both of these elements by themselves. Okay. But eventually, in order to finish our finite element analysis, we are going to have to assemble both of these into the same system. And so eventually, you know, we want to put both these element stiffness matrices into the same kind of framework. But right now, as we have it, we can't actually do this, because if we assemble, you know, one element stiffness matrix was kind of constructed under one coordinate system. The other one has to be constructed in a different coordinate system. And so when you assemble it, it's going to be inconsistent. And so kind of the assumption that we make, or the thing that we have to do, is that when we assemble element stiffness matrices, they have to be under the same coordinate system. Okay. And so you can't have, you know, element stiffness matrices in different coordinate systems, assemble them into the same one and expect to get, you know, good results. And so, you know, we have to assemble them under the same ones. Okay? And so what we're going to do is, you know, we need to find a way to basically use the transformation matrix that we just found to transform the element stiffness matrices into a consistent stationary coordinate system. Okay? And so that's what we're going to do. So we're going to use the transformation matrix together with the element stiffness matrix for the truss that we already know, and we're going to transform that into the stationary coordinate system. Okay. Any questions on this so far? Does that kind of make sense about, you know, why we need the transformation matrix for 2D problems? Okay. All right, so let's go ahead and do it. And so let me go ahead and do this. And so let me draw a typical truss element. Okay. So let's say that this truss is angled with respect to the horizontal by theta. Okay. And so if we were to draw a coordinate system local to this element, you know, we would have the x prime direction going this way. We'd have the y prime direction going that way. Okay. And so we can say if this is node 1, node 2, then we would have dx1 here and fx1 prime. Okay. And then on the right-hand side, we'd have dx2 prime and fx2 prime. Okay. So all of this is local to the coordinate, or local to the element. Okay. And so the element stiffness matrix element stiffness for this element stiffness matrix for this element would be F1 x prime, F2 x prime is equal to AE over L times 1 minus 1 minus 1, 1 times U1 x prime, U1, U2 x prime. So everything is in terms of the local coordinate system, because that's all we know so far, right? And so we only know how to form element stiffness matrices in systems that are local to the element. Okay. So what we want to do is we want to transform this into something that's in the stationary coordinates. Okay. Yeah. Oh, I'm sorry. In my notes I have U, but then I forgot that I'm using D for this ones. Yeah, thank you for that. Okay. And so we want to transform this into just, regular X, regular Y, without the primes. Okay. So to do that, the first thing we actually need to do is we need to augment this because, we're going to need to form the transformations in both X and Y. Okay. Okay, so I'm going to augment this with the Y prime direction. Most of these are going to be 0 because these are in directions, perpendicular to the element, but we need this in order to do the transformation. Okay. And so now we kind of transform this into from a 2x2 to a 4x4 system. So we have F1 X prime, F1 Y prime, F2 X prime, F2 Y prime. Okay. And so you can see I've added the Y prime directions to the Fs. Okay. When we do that to the matrix, we're going to add, everything that's going to get added is going to be added as a 0. So we have a 1, 0, minus 1, 0, 0, 0, 0, 0, minus 1, 0, 1, 0, 0, 0, 0, 0. And this is multiplied by dx, d1x prime, d1y prime, d2x prime, d2y prime. And so all I did for that step is I've added the y prime directions, but because this truss is not going to deform in the y prime direction, I've just added zeros to all those entries. Okay. Okay. So now that we have this system here, now we have to start transforming. And so I've circled the 2 vectors here, and I've circled those 2 vectors because I want to let you know that's what we need to transform. Okay. Because all those vectors right now have the prime directions, right? So they're F primes and D primes. And so we need to use the transformation matrix to transform these primes to the regular. Okay. And so to do that, let me go ahead and remind you of our transformation matrix. Okay. And so our transformation matrix is cosine theta, sine theta, minus sine theta, cosine theta. Okay. This is ux, uy is equal to ux prime, uy. Okay. So that's the transformation matrix that we derived earlier today. Okay. What if I replace this? So instead of ux, uy, why don't I replace this with f1x, f1y, and this will become f1x prime, f1y prime. Okay. In a similar way, let's form the same transformation matrix, but for node 2. Okay. And so I'm just gonna start to use shorthand here because it gets to be a lot. And so instead of cosine theta, I'm just gonna write C. And instead of sine theta, I'm just gonna write S. Okay, so our transformation matrix is CS minus S then C. Okay. And so we do the same for node 2. We have CS minus SC times F2x, F2y is equal to F2x prime, F2y prime. Okay. Okay. And so we know that we can use this transformation matrix for each node individually. But what I'm going to do is I'm going to combine these into a single augmented matrix. So if we combine these two into a 4x4 matrix, we're going to have C S minus S C 0 0 0 0 0 0 0 0 and C S minus S C. Okay. And then we multiply this by F1x, F1y, F2x, F2y is equal to F1x prime, F1y prime, F2x prime, F2y prime. Okay. And so you can see I kind of did that augmenting thing again, where I've added a bunch of zeros to the places that are, that are not important. Okay. And so I placed the zero strategically here so that, node 1 only acts on node 1 stuff and node 2 only acts on node 2 stuff. Okay. All right. And so let's look at this. And so we have this vector right here. Okay. And so those are all the prime candidates. And so let's compare that to this. Okay. So I've circled them both in red to show you that they're the same thing. And so what we can do is we can substitute this entire thing here. You can substitute that entire thing there in for the prime variables, okay? And what that will effectively do is that it'll effectively eliminate the prime coordinates from our expression here, okay? So that's good. Okay, so I'm not going to write it all down just because it gets to be a bit too much, but what I'm going to do is I'm going to call this entire matrix, this 4x4, I'll call it T. T for transformation. Okay. And I'll call this vector here. Actually, no, let me call this vector here. This vector here for the F's without the prime, I'll call this F vector. Okay. And so if we substitute those in, okay. And I'm going to do the exact same thing for the D primes as well. And so, for the D's, we have the same thing. What we get is the following. And so on the left-hand side, we get T, F, okay, this is equal to K. Let me add underlines here to indicate matrices. Okay, so this K right here, this is the element stiffness matrix. In the local coordinates. And so that's our AE over L, 1 minus 1 minus 1, 1, okay? Augmented, of course. And then we're going to multiply that by T times D, okay? And so this T times D is the transformed E prime vector. Okay, we're almost done, I promise. And so the last thing we need to do is we need to take this T vector here because it's kind of sitting out there on its own, and we need to move it to this side. And so the way we do that is we multiply by T inverse, okay? So if we do that, we have F by itself times T inverse times K times T, put this all in parentheses, times D vector, okay? All right. And so that quantity that I put in parentheses there, this quantity here is a 4x4 matrix, which is from T inverse, multiplied by the augmented K, the augmented element stiffness matrix, which is also 4x4. And this T transformation vector here, non-inverse, is also a 4x4 matrix, okay? And so when you multiply all this together, it's a ton of algebra. I'm not going to subject you to that, and so we're not going to work it out by hand, but I will give you the final result here, okay? And so these three matrices combined together, when you multiply them, this becomes the element stiffness, the 2D element stiffness matrix for truss in the stationary coordinates. Okay. And I'm going to just give that to you right here. And so the K stationary, I'll call it KS. This is equal to AE over L, okay, times a ton of cosine and sine terms. And so we're going to have cosine squared, cosine times sine, minus cosine squared, minus cosine sine. And then we have sine squared, minus cosine sine, minus sine squared, and cosine squared, cosine sine, sine squared, okay? And so we have a 4x4 matrix. The reason I only put the upper half of the matrix, the top right, upper half, is because this matrix here is symmetric. And so this bottom half here is going to be the same as the top half. But just for completeness, I'm going to go ahead and write in all of them for you, just so you can kind of just plug in when you're doing problems. Okay, so that's your element stiffness matrix for the for 2D truss in the stationary coordinates. Okay, and so if you use this element stiffness matrix for a truss, you can then we can solve 2D truss problems now, and we can run through our 5-step finite element process as we did before. Granted, we use this element stiffness matrix. Okay. And so, of course, first thing you'll notice here is that this is a ton of work just to, it was a ton of work just to get here, but it's also going to be a ton of work to actually use this in problems because, if you compare it to our lowly 2x2 element stiffness matrix, a 2x2 element stiffness matrix only had 4 entries. And so when you go up to 4x4, now we have 16 entries in this element stiffness matrix. And it's a lot more annoying to compute because we have cosines, sines just going all over the place. And so 2D problems are a huge step up from 1D in terms of, I mean, definitely in terms of the amount of computations and the amount of work that you do. And so, you want to make sure that you're kind of mentally prepared to do these problems because they can take a while. And if you make a mistake, it can be very frustrating to try and find out, where the mistake is. And so, I just kind of want to warn you guys ahead of time. Okay, so that was a very long derivation. And so are there any questions on this before we do a couple examples? Okay, all right, so for the rest of today, I want to do some examples. First, I want to show you an example of how to actually compute this. And then we'll do an example of putting this in practice into an actual FEA problem. Okay, so let's do an example of just how to compute this first. And so let's consider the following bar element. And this truss element is tilted 30 degrees with respect to the horizontal. We have values of the parameters. And so we know the cross-sectional area is 2 inch square. The length of the truss is going to be 60 inches. And the Young's modulus, we'll say, is 30 times 10 to the 6th PSI. Okay, and so visually, it looks like this. And so we have our truss element here. This angle here is 30 degrees, okay? And so what we want to do for this element is we want to compute its element stiffness matrix. And of course, because it's 2D, we want to compute its element stiffness matrix in the stationary coordinates. And so we're going to plug, and so we're basically just going to be plugging and chugging into this gargantuan matrix right here. But the reason I'm doing this example here is I want to show you guys kind of my strategy that I use to approach this. Because if you're just kind of blindly plugging and chugging, it's going to take you forever, and and you're probably going to make a mistake just because there's so many calculations. So there's kind of a strategy to this, and kind of an approach to one, save you some time, but two, also kind of minimize some mistakes. Okay, so let's go ahead and start. And so the first thing I like to do is that based on the angle that we have here for the element, I like to compute the cosine and the sine of that angle just straight up. Okay. Okay, and so for this truss element, we have C, which is cosine of 30 degrees. And so cosine of 30 degrees is √3/2. Okay. And we have S. S here is sine of 30 degrees. And so sine of 30 degrees is 1/2. Okay. So that should be the first thing that you do, just because it's the simplest thing. And you're going to be plugging in a ton of C and S. And so if you kind of know what C and S is ahead of time and you write it down, it'll make it a lot easier to plug into the equation. Okay. Okay. So now let's compute the element stiffness matrix. And so the element stiffness matrix in the stationary coordinates is we have AE over L. And so let's go ahead and compute that first. And so the cross-sectional area here is 2 inch squared. Young's modulus is 30 times 10 to the 6th PSI. And the length of this is 60 inches. Okay. And so if we compute that, top, you can see we have 2 times 30, which is 60, and that's going to cancel out with the 60 on the bottom. And so what we have is 10 to the 6th pound per inch. Okay. Okay, so that takes care of the coefficient out in front. And so next thing we're going to do is we're going to start to plug in for all the cosine and sine terms. Okay. All right. And so for this, it really helps if you kind of write it down on, maybe a Post-it note or maybe a piece of paper next to you, so you can kind of plug in and kind of look at both at the same time. Okay. But well, I have that here because I have the lecture notes, but I'm going to scroll up and down here just so that you can see. Okay. Okay, so in the top left, we have cosine squared. And so cosine squared is going to be √3/2 squared. Okay. Next, we have cosine times sine. And so cosine times sine is √3/2 multiplied by 1/2. Okay. Next, we have √3/2 squared with a negative sign out in front, because that's minus cosine squared. And then we have a minus cosine sine. So we have minus √3/2 times 1/2. Okay. So that's the first row in the matrix. Okay. Okay. And so the first trick that I'll tell you is that, remember, this element stiffness matrix is symmetric. And so use that to your advantage. And so you shouldn't have to manually compute every single entry in the matrix. Okay. And so we know for a symmetric matrix, what we can do is we can take this first row and then write it into the first column. Okay. And so this first entry right here, this √3/2, the very first entry, √3/2 squared, that's going to stay there. Okay. Next thing I'm going to write down is √3/2 times 1/2. Okay, because that's that entry right there. Next, I'm going to do minus √3/2. Minus sign goes out in front. Minus √3/2 squared, because that comes from that entry. And then finally, we have minus √3/2 times 1/2. And that comes from that entry. Okay. And so when you're computing this, use the matrix symmetry to your advantage. Okay. All right. So, basically what I do is that as soon as I compute a row, so I start from the top and I write the first row. And as soon as I write the first row, I write the exact same entries into the first column as well. Okay, so I kind of take that first row and kind of rotate it down just like that. Okay. All right, now we get to the next row. And so the next row starts on the diagonal term, which is sine squared. And so sine squared here is 1/2, okay, squared. Then what we have is a minus cosine sine. So we have a minus √3/2 times 1/2. Okay. And then we have a minus sine squared. So we have minus 1/2 squared. Okay. I'm going to do the same thing I did for the first row. So as soon as I finish that row, I'm going to write that row into the column. Okay. I'm just going to finish this out. And so we have a cosine squared on the diagonal. So that's √3/2 squared. And then cosine sine, so that's √3/2 times 1/2. Okay. It's √3/2 times 1/2. Okay. And the bottom right, we have sine squared. So we have sine squared, which is 1/2 squared. Okay. So be methodical about it. So kind of kind of do it systematically. And so I think if you look at it as a whole, it's intimidating because it's a lot of terms, but if you are kind of methodical about it, it becomes a lot easier. Okay, and so the last step here is just to kind of simplify all this math. And so B of KS, okay. Out in front here, we have a 10 to the 6th, okay. And so if we do all those things there, we're going to have a 3/4, 3/4, minus 3/4, minus √3/4. And once again, I'm going to write that into the column. And we're going to go ahead and continue this. And so we have 1/4 minus √3/4 minus 1/4. Let's go ahead and finish it out. Okay. So that right there is our element stiffness matrix in the stationary coordinates. Okay. If you wanted, and you would have to do this if you want to do assembly, you can take that 10 to the 6th and distribute that through to every single entry in the matrix. But if you're just computing the element stiffness matrix, just for the sake of simplicity and for saving you some work, you can go ahead and leave it on the outside, just like that. Okay. All right, so that's kind of my strategy, and that's kind of my approach to plugging in for these element stiffness matrices. Okay. Any questions on that example there? Okay. All right, so we have about 15 minutes left, 13 minutes left. And so what I'm going to do is I'm going to start the next example. So the next example is going to be a full 2D truss problem. And so we'll go through the process of computing the element stiffness matrices, assembling them, applying boundary conditions, and solving. And so, we're not going to have, we're not going to have enough time to do the whole example, but I'll go ahead and start it today, and then we'll finish it up on Tuesday. Okay. And before I start this example, whenever you're doing kind of a full finite element problem, it's kind of useful to remind ourselves, what the 5-step process is. Okay? And so the first step is to discretize the geometry and to label the elements and nodes. So remember, it's discretize, that's label. Okay. Second step is that once you've labeled all the elements and nodes, is to compute the element stiffness matrices for all the elements. Okay. Step 3 is to assemble. Once you have all the individual element stiffness matrices, you need to assemble it all together into one global linear system in order to solve it. Okay, so 3 is assemble. 4 is to apply boundary conditions. So boundary conditions are going to modify your global linear system and make it solvable. And then step 5 is to solve. And so the solve step, remember, you're usually going to do that in MATLAB, especially for these problems, because you're going to see our global linear system is going to be 8 by 8. And so unless you really enjoy solving a system of 8 equations and 8 unknowns, I would recommend that you solve it in MATLAB. Okay. Okay, so that's our process. And so nothing's changed about the process. The only thing that's going to be different is step 2, which is going to take a lot more work now because, we have 4x4 on the stiffness matrices. Okay, and so in this example, let's consider the following assembly of trusses and springs. So let's see. All up here, we have one truss bar that kind of comes vertically down. Okay. We'll call this element A. We have a spring that goes like this. That element B. And then we have another truss bar that goes horizontally like this. Okay. And that's element C. Okay. And so let's go ahead. So I've already labeled the elements there. So we have elements A, B, and C. Let me label the nodes. And so this will be node 1, where they all kind of converge. We have node 2 up top here. We have node 3 that's attached to the wall for the spring, and node 4 on the right side of the truss bar. Okay. We need the geometry for these, and so this angle right here, the angle that the spring makes with the horizontal is 45 degrees. And then the angle that the second truss bar makes with the spring is another 45 degrees. So the total angle for element A is a right angle, so it's 90 degrees. Okay. We have our load. I always forget to put the load, but I'm not going to forget this time. And so our load here is going to be 10,000 pounds. So that's going to be pointed vertically downwards. Okay. And so we have, maybe something that's really heavy hanging from node 1. Okay. And then we also need the properties for these elements too. And so for elements A and C. So these are our truss elements. And so we're going to assume that their properties are identical. And so they have a Young's modulus of 30 times 10 to the 6th PSI. They have a cross-sectional area of 2 inch squared. And they have a length of 10 feet. Element B is a spring. And so the only relevant property for element B is the spring constant. And so the spring constant for element B is going to be 250,000 pound per inch. Okay, so that's the setup for the problem. And so our goal in this problem is to use the finite element process. In particular, the direct stiffness method, the direct stiffness approach, to compute all of the displacements at the 4 nodes. Okay. So that's the setup for the problem. And so we have 3 elements here. what you'll see is that because one of the elements is horizontal, the other is vertical, that's going to save us a lot of work. And so, it's not going to be nearly as painful as the last example, but it's still going to be quite a bit of work. But, this is kind of what we're working with. Okay. Any questions on this? Okay, so let me go ahead and write the element let's go ahead and start with the element stiffness matrices, okay? Because we've already discretized this structure, and so we've already broken it up into elements, and we've labeled everything. And so the next step is to write all the element stiffness matrices. Okay. All right, so let's start with element A, and that might be all that we have time for. Okay. And so first thing we need to determine for element A is we need to determine its angle. Okay. And you have to be a little bit careful here because when we put in the angle, remember the angle that we put in is with respect to the positive x-axis. Okay. And so it might be tempting from the figure to say that, the angle that element A makes with element B is only 45 degrees. And so you might be tempted to say that, the angle for element A is only 45. But, if you look at a horizontal element, which is element B right there, you can see that we have to travel 90 degrees to go from horizontal to element A. Okay? And so the total angle for element A, therefore, is actually 90 degrees. Okay, so you have to add both the 45 degrees. Okay. And that point right there, when we say that the angle has to be with respect to the positive x-axis, that's going to be really important, later on. So this example is not going to be as important, but that's going to be crucial later. Okay. Okay. And so when our theta is 90 degrees, this actually simplifies things quite a bit because the cosine of 90 is 0 and the sine of 90 is 1. Okay. So that's really nice because when we have a 0 here, this means that any entry in our element stiffness matrix with the cosine, we're just going to say it's going to be 0. Okay. All right, so let's first compute the AE over L. And so the AE over L for this one is what was it? It was 2-inch square. E is 30 times 10 to the 6 psi. And we're going to divide this by 10 feet. 10 feet is 120 inches. And so if we do this, we get 5 times 10 to the 5 pound per inch. Okay. And so the element stiffness matrix of element A, okay, this is equal to 5 times 10 to the 5th. Okay. Then we're going to start filling things in here. Okay. And so if you look at the element stiffness matrix, we have a lot of cosine terms. And so anything with a cosine, I'm just going to set it equal to 0. Okay. And so actually the entire first row is all going to be 0. Next, we have sine squared, which is 1, and 0 minus sine squared, 1. Another row of zeros. Just like that, okay? And so we have a ton of zeros, which is nice. And don't forget, the last thing that you have to do with the element stiffness matrix is you have to indicate which nodes that element acts on. So element A here, it acts on nodes 1 and 2. And so on the vector that we multiply it by, it's going to be d1x, d1y, and then d2x, d2y. Okay. Okay, so that's just about all we got time for today. And so are there any questions on this before we head out for today? Okay, all right. And so on Tuesday, we'll pick up with this example here. And so we'll go ahead and finish this out. There's a couple extra concepts that I want to go over in terms of trusses. And so we'll go over that as well. Okay. And then we'll keep on going. So I hope you guys enjoy your weekend. Remember, project is due in about 10 days. And so make sure you're working on that. If you have any questions on the project, you want me to look at anything, you're running into any issues, feel free to drop by office hours anytime. Or if you want to email me, I'm always happy to answer questions on email. Or if you want to set up an appointment with me, that's fine too. Okay, so make sure you guys are working on it, and don't be afraid to reach out if you hit a snag. Okay, so thank you everyone for coming today. Hope you guys enjoy your weekend, and I'll see you on Tuesday.
Curiosity, did you go straight into teaching after school, or did you
I did.
you didn't go like industry or anything like that?
No, well,
Okay.
I had internships in industry, but then just went straight.
Okay. I'm like stuck, so I have like 2 offers. I have an offer, but one of them's out. So I'm offered the ones that matter is Northrop and Lockheed.
Nice, that's awesome. Congrats.
Thank you. So Northrop is in Palmdale,
Uh-huh.
and Lockheed's in Dallas, Texas.
Oh,
And so I'm like
that's
trying to be,
tough.
I'm trying to be like, oh, this is like, and like my decision's kind of due by Saturday.
Oh,
Yeah.
wow.
So
That's
they give me
really
like, well, I mean, on a technicality, they're due next Saturday. So like,
Yeah.
I really need to have another week.
Yeah.
But my first one that I'm not really gonna take, it ends this Saturday.
I
I want to
see.
use that as like leverage to like
Sure.
try to counter off or whatever.
Yeah.
But I was like, I don't know if I can handle moving to Texas. I don't know anybody in Texas. But also
Well,
like that was like the best career opportunity. Like Lockheed, from what I've heard from my talk to people, it seems like all their just like opportunities and then all their compensation and everything is like Lockheed's like the best. That's what I've heard. And so I'm
yeah,
like,
no state income tax in Texas too.
that's what I've been
That
laying
helps,
out. That helps a lot.
that's pretty clutch too.
Yeah, well, the funny thing is like, all like the numbers are almost the same, but the funny thing is like, the same in California versus the same in Texas is so different.
It is.
It's
Cost of living there is like so much more too.
Yeah, so I'm like, trying to figure out what to do.
Oh, man. Well, it's a good problem to have.
Yes. So, we'll see.
Yeah.
Thank you.
Yep. I have some friends that live in Austin actually. It's they really like it. Always make fun of me because they have no state income tax, and we have massive state income tax. All right, Zoom people, any final questions? The next class is rolling in, so. Oh, yeah, it's been growing a lot, that I've heard. Okay, all right, so I'll see you guys next week. Nice.